All right, the expression power series is another way of saying Maclaurin series. And we're going to be working from this one. We've already done this. 1 over 1 minus x turns into this Maclaurin series. So if we start with something that looks like this, then I want to manipulate it to be able to use this x to the n. So let's look at this. So I have this function 4 over 1 plus x cubed. So this 4 can be pulled out in the front, right? That's not a big deal. If I wanted to make the denominator look like 1 minus a quantity, I could say 1 subtract x cubed. So I'm manipulating what I have to use what I know. So here I go. So this sum, I can put the 4 on the outside or the inside, it doesn't really matter. But this x gets to the nth power. So this is my x in this case. So negative x cubed to the nth power. So again, I'm just using this expression that looks very much, let me get rid of some of my marks here. So this expression looks very much like this. So I'm making it match, just like I did with the Maclaurin series with cosine and sine. So I rewrote this as 1 minus negative x cubed. So this is my x that I'm substituting into here. And the 4 just kind of carries along on the outside. So I'm going to simplify this because I'm going to need to in the future for what I'm going to do next. So this negative, or this n, distributes to the negative 1 here and to the x cubed. So be careful. This nth power goes to the negative 1. It's implied negative 1, right? And x to the 3n. So this is the Maclaurin series for this without having to do with the bunch of derivatives. So now the reason I've been having you simplify this is now we're going to use the Maclaurin series to integrate. Look at that. We're going to put this in the integral. So put this in the integral for negative 1 to the n, x to the 3n dx. Okay, so let's talk how it is we do the integral. So it's the x that I add 1 to the exponent, correct? So the rest of it carries along the summation n equals 0 to infinity, 4, negative 1 to the n. They all carry along. And now I integrate x to the 3n. So how do you integrate x to the 3n? You add 1 to the exponent and you put it over that same number plus c. So added 1 to that exponent and put it over that same number. So I just integrated the Maclaurin series where I could not have done the integral any other way. All of our integration techniques left us nothing for this. So that's why we wanted to do the Maclaurin series. So it's kind of a two-step process, right? So if I find the Maclaurin series for this, then I can use it in the next step to integrate. All right, so let's pull this over here. So this is like saying 3x times 1 over 2 minus x to the 4th. All right, so what do I know? I know that I have to have a 1 here and I have to have a subtract x. So first off, I have to get a 1 here. So I can't do subtraction, but what I'm going to do is I'm going to multiply numerator and denominator by 1/2. So this 1/2 here, I'm going to multiply times this, so I get 3/2 x. This 1/2 I'm going to distribute through here. So I get 1/2 times the 2, that gives me the 1 that I want. This 1/2 times here, I get negative x to the 4th over 2. So these are the two non-negotiables. I have to have a 1 and I have to have a subtraction. Once I have those, I'm good to go. So summation n equals 0 to infinity. This 3/2 x carries along, and it's this x to the nth power. So this x to the nth power. So let's invest time right now simplifying this so that when I want to take the integral in the next step, it's all good to go. So n equals 0 to infinity, 3 has x. So let's first distribute this nth power. So be careful, it has to go to both. So I get x to the 4n, and this n has to go to the power of 1 on the 2, so I get 2 to the n. So if I wanted to combine things, so let's see, I have 3. This x and this x to the 4n makes x to the 4n plus 1. This 2 and this 2 to the n makes 2 to the n plus 1. All right, so now let's put this in the integral. So I have 3 x to the 4n plus 1, 2n plus 1 dx. Okay, so remember, if I'm integrating with respect to x, x is the only thing that's going to get their exponent raised. So here we go. So summation, so taking the integral, right? Carrying along the 3, the 2 to the n plus 1, those are constants as far as x is concerned. Now I'm going to add 1 to the exponent. So I get x to the 4n plus 2 divided by 4n plus 2 plus c. Okay, so here I'm not doing it in 2 parts. I'm expecting you to figure out, oh right, I need to make this a Maclaurin series, then I'll integrate it. So you know you have to have 1 over 1 minus x to get x to the n, right? Kind of restating what I had in the beginning. So let's take this fraction and rewrite it. So I'm taking it out of the integral to just kind of play with it. So this is going to be negative x squared to the nth power, because they've got the negative, I've got the 1, so this is my x to the n. So be careful, this nth power distributes to both of these terms. So there is a negative 1 that gets the nth power, and then I get x to the 2n. All right, so now if I put it in the integral, negative 1 to the n, x to the 2n dx. It's an indefinite integral. Negative 1 to the n carries along. It's just this x term that I'm increasing the exponent on. So put the 2n down here, plus c. So I did everything all together. So you recognize what I want to do, rewrite it using my pattern, and then take the antiderivative. All right, so yet another Maclaurin series to get to know. So this is x to the 2n plus 1 over 2n plus 1. Remember, sine has 2n plus 1 factorial, so it's different. So let's go do this. So first, let's find what this is equal to. So that's going to be negative 1 to the n. Instead of x, I'm going to put in 2x. And the 2n plus 1 carries along in the denominator. So, whoops, n equals 0. So I have negative 1 to the n. So again, separate this exponent over the 2 and the x. So I get 2 to the 2n plus 1, x to the 2n plus 1, all over 2n plus 1. All right, so now I'm going to take the antiderivative of this. So take the time to put it in the integral. Okay, so remember, it's just x that I'm increasing the exponent on. So the sum with the negative 1 to the n, the 2 to the 2n plus 1, the 2n plus 1 in the denominator, those all carry along. And now I'm ready to add 1 to this exponent. So adding 1, I get 2n plus 2 and 2n plus 2 plus c. Okay, last one. So this one here, I'm going to be multiplying my arctangent by an x squared. So starting off with what we know. So I'm going to go slow. I'm going to take the steps. So arctangent of x squared. will give me negative 1 to the n, x squared to the 2n plus 1 over 2n plus 1. So negative 1 to the n, x to the, distribute this, 4n plus 2. So that's arctangent of x squared. Now I'm going to multiply by this x squared. So if I take this, negative 1 to the n, x to the 4n plus 2 times x squared, then what that gives me, negative 1 to the n, it's kind of messy there. So I'm adding these exponents, right? X to the 4n plus 4 over the 2n plus 1. Okay, so there's my function. So now I want to integrate that. Dx. Again, it's just the x, and I'm going to be increasing the exponent on. So I'm going to carry this negative 1 to the n along. This 2n plus 1 gets carried along. Now I'm ready to add 1 to the exponent, so I get 4n plus 5, 4n, whoops, sorry, that's really messy, 4n plus 5 plus c.